In this module, we will see some more examples of sequences and convergence, but this time we will study some special sequences that are of great importance throughout your studies and analysis. So, let me recall a definition. Recall that a polynomial is a function f from R to R that is of the form ad x bar d plus ad minus 1 x bar d minus 1 plus dot 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 a naught. Okay, and here for definiteness, where we assume ad is not 0. Okay, and this d is called the degree of the polynomial. Now I'm going to do some studies of sequences that involve polynomials. Okay, so first example, you might have heard of this colloquial expression that an exponential grows faster than any polynomial growth. So let's see how to translate this in terms of sequences. Let a be greater than 1, be a real number. Then limit n going to infinity a power n by n, this in fact is equal to plus infinity. In other words, this sequence a power n by n diverges to plus infinity. That means the growth of a power n cannot be counterbalanced by the growth of n. A power n sort of grows much faster than just n. How do you show this? Well, again, we are going to use the binomial theorem. What we do is write a to be 1 plus b, where b is greater than 0. Okay, consider 1 plus b the whole power n by n. This you can see is actually 1 plus nb. Now I need to write one other term because there is an n in the denominator. So I would need to go further along in the binomial expansion than what was needed the last time when we just considered the sequence a power n with no n in the denominator. Okay, plus some other terms, I don't care about what they are, divided by n. Now why did I consider till the level 2? Well, simply because this I can write is greater than or equal to 1 plus b plus n minus 1 b square. I forgot a by 2 here. The binomial coefficient will actually have by 2. So let me just write that down, by n. So n minus 1 by 2 b square. So I'm ignoring all the other terms. Okay, and since I'm allowed to do all this because every single term here is positive, and this is certainly going to be greater than or equal to n minus 1 b squared by 2. Okay, and this last thing converges, or rather diverges to plus infinity. Okay, so this shows the claim. Okay, so we have seen that a power n goes faster than n, but originally I made the remark that a power n goes to infinity faster than any polynomial. How do you deal with that? Well, that's the second example, which is one layer even more complicated than what we have seen. That is limit n going to infinity a power n by n power k is also plus infinity, where k is a natural number. Okay, so this time we are dividing by any higher order monomial. Now, how do I show this? Well, this is slightly trickier, but it's exactly the same idea. Write a as, again a is greater than 1, write a as 1 plus b and b is greater than 0, and look at 1 plus b the whole power n. Okay, look at 1 plus b to the whole power n when n is greater than k. When n is greater than k. Now, how will the binomial expansion look like? This is nothing but 1 plus nb plus dot 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 some other terms, and I focus on one particular term, and you should be able to guess what this particular term is. It is that term which has b power k minus 1 as the power. B power k plus 1, not k minus 1, b power k plus 1 by k plus 1 factorial plus some other terms. So I focus on this particular term which has b power k plus 1 in it. Okay, so this is what 1 plus b power n will be when n is greater than k. Now I have to divide this. I have to divide this by n power k. Okay, I want to consider this, and I want to show that it's greater than or equal to some quantity that sort of goes to plus infinity. Okay, now how do I do that? Well, observe that every term here is also positive, so I can ignore all the terms except the term that I'm really interested in, which is this. I can ignore all the other terms. Now if you look at this term and expand out n into n minus 1 dot 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 n minus k, it is easy to see that this whole thing will be greater than or equal to some n power k plus 1 divided by k plus 1 factorial plus terms with lower powers of n, and the whole thing gets multiplied by b power k plus 1 and divided by k plus 1 factorial. Okay, so what I have done is I have focused on one of the terms, the one having b power k plus 1 as the coefficient. Then what I am doing is this binomial coefficient that comes, I am expanding that, and I notice that there will be one term which has k power 1, that is one when you multiply all the n's together. There are k plus 1 of them, and then oh sorry, I made a mistake here. This is n power k. Okay, so when you do this division, it's easy to see that what you will be left out with is n by k plus 1 factorial into b power k plus 1. That will be the first term. Then there are all lower order terms whose coefficients could be very complicated, but I don't really care about the coefficients. All I care about is how do they look like. And you can see that I can just take everything outside and it will look like c1 by n plus dot 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 c k plus 1 by n power k plus 1. Okay, what have I done? Well, there is an n power k coming in the denominator, and that will cancel off with n power k plus 1, and you will be left with an n by k plus 1 factorial b power k plus 1. Now the next term will involve n power k, right? And when you divide by n power k, that will be gotten rid of. But I am still taking an n outside, so you will be left with some coefficient c1 by n. Okay, so originally this term had n power k that got cancelled out, but there is an n in the denominator because I want to keep one n outside. You will understand in a moment why I want to do that. And similarly, the final term will be a constant term out of which I am dividing an n power k and I am taking an n outside, so there is an n power k plus 1. Okay, and this 1 accounts for the very first term, which is this n power k plus 1 by k plus 1 factorial into b power k plus 1. Right? Now, why did I do this? Well, I did this because now I can just say all of these terms, irrespective of what the coefficients c1 to ck plus 1 are, all these terms go to 0. All of this converge to 0. Okay. So, I am just left with n by k plus 1 factorial times b power k plus 1, and this clearly goes to plus infinity, diverges to plus infinity. Okay. So, what we have shown is that 1 plus b the whole power n by n power k is in fact greater than or equal to a quantity that goes to plus infinity. So, 1 plus b the whole power n by n power k diverges to plus infinity as required. Okay. So, even when you take an exponential and divide by a higher degree term, you still get divergence to plus infinity. Now, example 3, as you can guess, and it's going to be an exercise for you. Exercise. Let P be any polynomial. Show that limit n going to infinity of a power n by p of n a greater than 0. This is plus infinity as usual. Okay. Excellent. So now we have seen some examples involving polynomials and exponentials. Now let's see some more sophisticated examples involving exponentials. Before that, let me just make a remark. If a is a real number, then we all know what a power n is. This is just a n times, right? And a power minus n is just this 1 by a power n. Okay, this is all valid when n is a natural number. Okay, now what happens if the power you take a power r, where r is a real number? Now this can be defined in several ways, but the most elegant way is to do it via exponentials and logarithms. Okay, now how do you do that? Well, let's assume that you can take log a power r. Okay, when can you do that? You can do that whenever a power r is greater than 0. Whenever a power r is greater than 0, you can take log of a power r, and we know that this becomes r log a. Okay, so we can just reverse engineer and define a power r to be exponential of r log a. Okay, and this will make sense whenever log a makes sense. Okay, in other words, whenever a is greater than 0. Now, I have not yet defined what the exponential and logarithm are. We will do it later in the course, but I just want to make a remark that this is the definition of exponentials that we will take in this course. Okay, so note that r could be anything, positive, negative, anything, and check that this definition agrees with what you already know. What do I mean by this? For instance, a power 1 by n should be nth root of a, for instance. So please check this. This is the definition of exponential. So now let me give some more examples of special sequences. So this is example number 4, I believe. If p is greater than 0, then limit n going to infinity 1 by n power p is equal to 0. And I'm going to leave this as an exercise for you. This is not at all hard. We have already seen what happens when p is 1 and what happens when p is 2. Okay. Similar remarks will apply even for this p being any real number greater than 0. Okay. So that's one more example that I want you to do as an exercise. Example number 5. If p is greater than 0, then limit nth root of p, n going to infinity, is actually 1. When you take a positive number, real number, and iteratively keep taking the nth roots, you get closer and closer to 1. Okay. Now, how are you going to show this? Well, what you do is, you do a particular trick. Suppose you want to show that xn converges to 1, then one strategy that you can adopt is to see that this is same as showing that 1 minus xn converges to 0, right? It's exactly the same thing in a different form. Okay. So now what I'm going to do is, of course, I can also say xn minus 1 converges to 0. You can do one of these also. Instead of showing xn converges to 1, you can show that xn minus 1 converges to 0. So what I'm going to do is, first assume p is greater than 1 and set xn to be nth root of p minus 1. Okay. Then xn is greater than 0. Why? Please think about why this is true. Okay. Now I want to show that this quantity xn converges to 0, right? Now what do I do? How do I approach this? Well, observe that 1 plus xn, the whole power n, is nothing but p, right? Again, by the binomial theorem, we can write 1 plus n xn is less than or equal to 1 plus xn, the whole power n, which is equal to p. Okay. In other words, 1 plus n xn is less than or equal to p. Right? Or xn is less than or equal to p minus 1 by n. We already know that 0 is less than or equal to xn. Combining these two, we see that xn converges to 0 by the squeeze theorem. Okay. So we were able to prove that xn converges to 0, and therefore nth root of p converges to 1. So again, this is very similar to the proofs we have seen earlier. We just use the binomial theorem. Okay. Now on to the next example, which is example number 6. We do the same thing that we have been doing, except with a more complicated twist. Nth root of n converges to 1. Okay. Again, to tackle this, we will transform the sequence into a sequence that we would want to converge to 0 by setting xn to be nothing but nth root of n minus 1. Okay. Again, xn will be greater than or equal to 0, and I want you to think about why this is true. Okay. Now n will again be equal to 1 plus xn, the whole power n. And now we expand this by binomial theorem. We will have many terms. I am interested in only one of them. This will be greater than or equal to n into n minus 1 by 2 times xn square. Right? Now, since n is greater than or equal to this, we can cancel off the n. We'll get n minus 1 by 2 xn squared is less than or equal to 1. In other words, 0 is less than or equal to xn is less than or equal to under root 2 by n minus 1. Okay? This will be valid whenever n is greater than or equal to 2. We have to be a bit careful because when n equal to 1, the denominator becomes 0 and this quotient doesn't make any sense. So, again by squeezing principle or squeeze theorem, xn converges to 0. Okay? Hence, nth root of n converges to 1. Okay? So, one final example, which is in fact I am going to leave it to you as an exercise. Okay? Analyze the sequence n factorial by n power n. This is a somewhat involved example. Please work this out in great detail. Okay. So this concludes this module on some special sequences, and you're watching this course on real analysis.